Okay, in this video we are discussing yield measures for money market instruments. Thus far in the previous videos we're focusing on the yield to maturity, which is a measure that's specific for bonds, capital market instruments. Now let's recall that the money market is composed of those instruments which have a time to maturity or tenor that is no more than 1 year. Typical examples would include things like treasury bills, certificates of deposit, bankers' acceptances, repo transactions or repo instruments that we talked about as well, commercial paper issued by companies, that's the kind of thing we're going to discuss here. Now, there are some very important differences that you need to know in how we compute yields versus in yield computation for money market instruments, computation for MM stands for money market instruments, and this is going to be versus the yield computation for bonds. Okay, now all of these will become more and more understandable as we proceed through the discussion and the questions that we're going to solve together. But let me say over here, yields on bonds, so that's going to be our classic sort of YTM measurement, and on the right hand side I'm going to say money market instrument, instrument yields or rate computations, right? The first one is this is really important. The first one is that yields on bonds, the yield to maturity, is always going to be an annualized yield, and it's going to be a compounded yield. Compounding means, this notion of interest on interest being accounted for in the computation, whereas in the case of money market instrument yields, they will indeed be annualized always as well. So we'll be doing this, but the way we annualize is rather simple. There is no compounding. No compounding. So simple interest only. And towards the end of the video I'll show you a way in which we can convert yields on money market instruments to a basis that is more comparable with bonds, where we will have an element of compounding using formulas that we've already encountered in previous lessons or in previous videos. Okay, so that's one difference, so to speak. Now the second difference is that when you compute yields on bonds, the YTM, you typically use a common periodicity. So they typically use a common periodicity, e.g. a periodicity of 2, which is quite popular, for example, in the UK and the US, where you typically have bonds paying semi-annual coupon. With money market instrument yields, you're going to have very different periodicities, because each instrument will have a periodicity that is a function of how much time it has to maturity, and that may differ quite a lot. You'll see that when we start doing computations, it will become more apparent. And the third point is that the computations for bonds make use of or are calculated, these YTMs, using standard time value of money functions, which we've been exploring in the previous videos. However, for money market instrument yields, you'll see that the computations utilize sometimes very elaborate formulas, non-standard sort of approaches. So often calculated using non-standard interest rates or approaches to interest rate computations, and you'll see what I mean in just a moment. So bear in mind these three, they will sort of resonate throughout the remainder of this lesson. Okay, so let's now get cracking with the actual computation of yields or expression of yields. The problem is there are two ways to do this, and also two conventions under which we can do it, which makes for quite a, let's say, wide range of approaches. But money market rates of interest, effectively money market rates or money market yields, may be expressed using two different bases or two different approaches. One is to express them as discount rates, and the other is to express them as something called add-on rates. Okay, and you've got to know both and be quite flexible in using both and actually converting between them as well, potentially. So this is a lesson or a section of the curriculum that you have to pay attention to. It makes for very sort of nice examinable material. There's a lot. Right. Okay. So when applying the discount rates approach, how do you compute the price of the security? Well, the price is going to be the PV, the present value. That's how it's denoted. And let me write the formula down first, and then I'm going to walk you through what each of the symbols actually means. So PV equals FV times 1 minus days divided by year times the DR. Now, FV here, so we know that this is the price today, right? The price at which the instrument should be trading, or is trading. The FV is, of course, future value, but this is the value at maturity. So basically the face value of the security, how much you're going to get when it matures. Now, days is the number of days between, in a transactional sense, settlement, when you have to pay for the instrument, and its maturity date. Because I'm assuming you're looking at the instruments today, its price, you're willing to buy it potentially, but you're going to settle, actually make the payment maybe in 2 business days, something like that. So how many days between that moment and the maturity date of the security? The year is, of course, the number of days in the year, and as you know, there are different conventions that we may use to approach that. It's either going to be 360 or the 365, sort of the actual, or 360. Now, DR stands for discount rate. That's the pretty obvious one as we're talking about discount rates. Okay, and look, I'll move on to add-on rates once we've finished with discount rates. I don't want to confuse you more than I probably already have. Okay, you need to potentially be able to make the switch between this expression and an expression for DR. One thing before I start converting this is, please note that at the very sort of center of all of this is the FV. It's the FV times something, which includes a negative expression for the DR. So we're sort of deducting the DR from the face value here, which is quite important because the face value is going to be our starting point, or our sort of main anchor in all this, in all of these computations. If we do just a little bit of, your book just goes straight to the expression for DR. I want to, those of you who are maybe not so mathematically savvy may have a problem doing this conversion, so I'm just walking through it. If this is not something you find difficult, well, don't worry about it. I'm going to say that PV equals FV, so I've basically taken this one and I've multiplied by a V, which is outside the bracket, minus FV again times days divided by year times dr. So hopefully you see what I've done. I've gotten rid of the bracket, the parentheses, and I've multiplied everything that's in the bracket out by fv. So if I bring the term that includes the dr over here over to the other side, I can say that dr times fv times days over year equals, I've left fv on the right hand side, fv minus pv. Hopefully that's still okay. And from this, it's a relatively short way now. dr simply equals fv minus pv divided by fv. See, I divided by this fv multiplied by year divided by days, because I'm effectively multiplying by the reciprocal of this fraction. Okay, well, what you need to appreciate about this formula, we're going to apply it in just a moment, is that at the bottom over here we've got the expression fv. So the whole rate of return, the discount rate, is computed on face value. So the interest or return is computed on face value, and we'll be talking much more about it in subsequent minutes of this video. The second point is that this is typically used, this approach, for specific instrument types, such as commercial paper. It's also used for treasury bills. It's also used for bankers' acceptances. Now, you don't have to worry about this list. In the exam, they'll tell you which approach to use. You don't have to guess which one is applicable. And now let's actually get cracking with a question. Here we go. This is a question which will get us to use the discount rate approach to a computation of price. So we will be computing the PV in this little exam style question. Assuming a 360-day year, the price of a 90-day US Treasury bill with a face value of 1,000 quoted at a discount rate of 3.46% is closest to. Okay, this is going to be relatively easy, assuming you know the relevant formula. So effectively, what we've got to do is look back at the formula. For present value, PV equals FV times, in bracket, 1 minus days over year times DR. Let me write that out again. PV. Okay, let me maybe write it slightly to the right here to make room for my calculator. PV equals FV times 1 minus days over year times the discount rate. Now, this may seem quite an abstract formula, but once you write it down a couple of times, it should become rather intuitive. So let's populate this with data before we actually do the computation. 1,000 for face value, then 1 minus days. Just take the days given, 90-day US Treasury bill. Let's divide that by 360, the assumed number of days in the year, assuming a 360-day year, and the discount rate 3.46, so times 0.0346. Let me start my recording on the calculator. Here we go. It's ready. So I'm going to deal with what's in the bracket first. 1 minus 90 over 360. Now multiply that by 0.0346 gives this much. If I times by 1,000, I see an answer of $991.35. That's absolutely in line with answer A here, which is very good. It's a simple problem, to be honest, and an easy one to solve in the exam if you face such a question. Right. Let's explore the formula just a little bit more. Over here, I have already made the conversion from the PV formula to the DR formula. So I'm now going to focus on that DR formula a little bit more. DR equals FV minus PV divided by FV. Remember, that was the very important characteristic of this formula, that in the bottom, in the denominator of the fraction, you've got FV times year divided by days. Let's explore this a little bit further. First of all, over here in the top of the fraction, in the numerator, FV minus PV, that's effectively your interest earned, how much you earn on a money market investment. The difference between the price at which you buy it, the PV, and what you walk away with at the maturity date, the face value. Okay, and please appreciate that we're relating this to the face value and not the amount invested. Traditionally, when you calculate a rate of return on an investment, you've got the price you pay for an investment in the bottom of the fraction. Here you've got the face value in the bottom of the fraction. And the logical sort of consequence of this, and hopefully you can appreciate this quite easily, is that the DR computation underestimates the rate of return earned by investors. Sort of the true rate of return earned by an investor, because in order to compute the proper rate of return, you would have to have the price paid, the PV, in the bottom of that fraction, and also it underestimates the cost of borrowing funds for the issuer. And that's obviously because typically PV is lower than FV, so the amount you put into an investment is lower than what you get out of it. Obviously, for DRs that are higher than zero, which is, I'm shooting this in 2024 nowadays, the case, but not so long ago, a couple of years ago, it wasn't the case, especially in the Eurozone, where we had negative rates. Now, the second point is this scaling factor over here, the year year divided by days. This is effectively how we extrapolate to a full year, how we annualize, okay? And this is effectively our periodicity. Okay, so what is the relationship between the full year and the number of days in the investment? If it's 90 over 360, if it's 360 days in the year and a 90-day investment, then we multiply by a factor of 4. That's the same as periodicity. And of the annual rate. And as you will appreciate, because each instrument has a different number of days in it, potentially there is a huge range of periodicities that we will encounter realistically with these types of investments in terms of how they are scaled up to a full year. Right, that's the first approach, the DR, the discount rate approach. Let's now say a few things about the second one and also do a question on it. Okay, the second one is referred to as add-on rates, and this one I hope will, for many of you, feel more intuitive. It may not, I'm not sure, but it should. Right, in this case, We calculate the PV by taking the face value, that's how much we'll get from the instrument at the end of its life, and dividing by 1 plus days over year times AOR. So you basically, if the AOR is a positive rate, you get something in the bottom of the fraction which is higher than 1. So the PV will be lower than a V, naturally. Now, once again, you can do a little bit of, let's say, conversion here. You can take what's in the bottom of the fraction on the right-hand side, take it to the left-hand side and say, ooh, this is, I don't know, days over year times AOR equal to FV divided by PV minus 1. Okay, hopefully that you're still with me on this one. And then you can say to yourself, well, AOR therefore equals, now I'm going to do a bit of a trick which your curriculum also uses, and it absolutely makes sense. If you've got FV minus PV on the right hand side here, I'm going to include the 1 in the fraction. 1 is basically, or PV, 1 is the same as saying PV over PV, so I could rewrite this as FV minus PV divided PV, because this alone, the PV divided by PV, makes for a 1. And once I've got that, I just need to multiply out by years over, number of days in the year over days. That's my expression for AOR, and you will hopefully notice that this time it's a very similar formula, to be honest, to the one we had over here for dr on the left hand side, right? Dr formula. The AOR formula is logically the same thing, but critically it's got PV in the bottom. Okay, so in this case, and this is why it should be more intuitive to most people, is that the interest or the return is in fact computed not on face value but on the amount invested. Okay, and the other point here is going to be that it is typically used for specific types of instruments, bank certificates of deposit, certificates of deposit. Also, it gets used in repo transactions. It also gets used for MRRs, market reference rates. So when market reference rates are computed or derived, they are typically done under this approach, under this sort of basis of computation. Right. Let's do a numerical question on this. So over here, down here, I've got a question which asks for the redemption amount for a $1,000 investment in a 180-day certificate of deposit. Well, certificates of deposit were one of the instruments I said would be computed typically using this approach, quoted with an add-on rate of 2.12% for a 365-day year. So what is the redemption amount closest to? Okay, as you can see, the redemption amount is not a nice round number. What is a round number this time around is how much you invest, the principal. However, the redemption amount is something you have to figure out on your own, okay, using the relevant approach. Let's go back to the formulas for just a moment. Right. This was the original formula for PV. It's FV divided by, this term. But as you can see, we can easily convert that to a formula for FV if we just leave FV on the right-hand side of the equation, or actually bring it over to the left-hand side, it becomes relatively simple. FV simply equals PV times, and I think this makes perfect sense to most people, 1 plus days divided by year times the add-on rate. Okay, you could go back and check that this is absolutely the same. The only thing that I've done is I've taken what was in the bottom of the fraction and I've multiplied both sides by it, leaving PV multiplied by the content of those parentheses to give us FV. Okay, this is a very natural way to compute future value. So let's just plug in the numbers. For PV, we've got, it's a 1,000 investment, so that's the amount put in. Then in the bracket we're going to have 1 plus 180 divided by 365 times an add-on rate of 2.12, so that's 0.0212. Okay, good. Let's see what that gives on the calculator. Once again, starting with the bracket, 1 plus 180 divided by 365 times 0.0212, close, press the equals key, and multiply by 1,000. That gives a nice answer of 1010.45, which is absolutely in line with answer B over here. That's nice and sorted. We've got the question done. Right. You know how to do the computations, or you will be able to do the computations, hopefully. However, you don't just need to be able to handle this numerically. You have to also appreciate some of the more kind of complex problems and some of the issues that we've got with these rates. So let me say issues. If you're potentially when trying to compare yields on money market instruments. So say you've got a yield computed like over here on a certificate of deposit, and you're told it generates 2.12%. At the same time, you're comparing it to the yield on a 90-day US Treasury bill, where we're told that the rate is 3.46. I mean, obviously one is lower than the other, but you can't just make a very direct comparison, because one is computed on the basis of the discount rate, whereas the other is computed on the basis of an AOR, okay, which leads to specific problems in terms of how the rate is stated, based on what. And the second problem is, in one computation we had 365 days, in the other 360, so you also have that problem, 360 versus 365 days, assumptions, conventions. Plus, look, typically with AOR, add-on rate, you will be quoted the amount of the initial investment, and you'll need to sort of work out how much you'll get back at the end of the instrument's life. Whereas with instruments where we utilize the discount rate, you'll typically be given the face value, and you'll have to work out the price today. So also coming with this, in the case of DR, amount provided is typically the face value of the security, like we had with the whatever it was it a treasury bill? Yeah, US Treasury bill here. Whereas with AOR based computations, you'll typically have the amount quoted typically being the amount invested, the price at issuance. So amount invested, which leads to a lot of problems when trying to make comparisons because everything is done on a different basis. So let me give you the recommended approach if you need to make a comparison. To make comparisons, what we need to do is in a way standardize the whole computation. And what we do is we take anything computed under the DR approach, the discount rate approach. So convert from DR to AOR. Okay, so that's the way to go, not the other way around. Obviously you could, but the recommended approach is to go this way, because the AOR approach is more meaningful from thinking in the sense of thinking about a rate of return on an investment, because it's got the PV in the denominator of the fraction, so it makes more sense. But AOR stated on a 365-day basis. So pretty much what we did over here, we computed an AOR where we assumed a 365-day year. So you would have to convert anything computed under the other approach to this similar to a basis that is in line with this. Once you do this, you get what's known as the sort of the bond equivalent yield, which is a term you've already seen in the previous videos on yield to maturity computations. So I want to do this conversion. I want to actually take the example that we had before, the first one, the question, where we had an instrument for which we were given the DR, the discount rate. We knew it was 3.46. It was a 360-day year, 90-day instrument. 1,000 was its face value. So I'm going to use that data to show you how the conversion would work. So just writing out the data again, the FV was 1,000, the DR was 3.46%. The number of days in the investment was 90, and number of days in the year was an assumed 360. Okay, that was the instrument to start with. Now, what you need to do first, step one, is calculate the PV. But using our classic DR conventions. Now, I know we've already done it because we've solved the question. The PV over here came in at 991.35. Yeah, I'm just going to do it again to show you the full process. So PV equals FV times 1 minus, because we're taking away from the FV, days divided by year times the DR. So, you know, very quickly, 1,000 times 1 minus 90 over 360, basically 0.25, right, times 0.0346. And let me get my calculator up and going, up and running again, and recording what's on the screen. Right here it is. So what's in the brackets? 1 minus 90 divided by 360 times 0.0346 equals, obviously, times 1,000. Okay, here we go again. That same answer, 991.35. So I know how much the instrument actually costs in the market, and that's critical. You need to know that first. And to compute the PV, you apply the relevant convention that is suitable for that security, or for that instrument. But then As part of step 2, you use that input to determine the AOR. Determine the AOR using 365 days. Okay. What was the formula for the AOR? Well, let's go back. Unfortunately, you have to be quite good with these formulas, but look, this was the intuitive formula. To compute AOR, you take the interest earned, the difference between face value and the price paid for the security, divide by the price paid, and scale up by a fraction that expresses year over days, but you have to now use a 365-day year. That's the catch. So AOR effectively equals FV minus PV divided by PV scaled by year over days, but here please use 365. Okay, so don't stick to the previous convention of using a 360-day year because it was given in the question. That was relevant for computing the price. Once you've got the price under the DR approach, you then scale up to get the AOR under a 365-day assumption. So FV 1000 minus the just a moment ago computed PV, so this goes over here and into the denominator of the fraction as well. And we scale up 365. Obviously it was a 90-day security, a 90-day investment. So hopefully that should be our result. Let's have a look. 1000 minus 991.35. Okay, divided by 991.35, and now multiplied by 365 over 90. Okay, it seems to be 3.5 something. I'm going to write this down in a sort of up to 3 decimal places, 3.539%. The reason why I wanted to do that is I just wanted to provide you with a bit of a check, to check if this is okay. We can easily take the 991.35, this amount, which is our PV, scale it up by multiplying by 1 plus 90 over 365 times the freshly computed add-on rate, 3.539%. You see, effectively what I'm doing here is I'm doing the same thing that we wrote out over, where did we write this? Wait, we did it somewhere. I'm not sure where now, sorry. Yeah, over here, apologies for that, where we were computing the FV. It was PV times 1 plus days over year times the AOR. Well, I effectively have done the same sort of computation here, but using the number 3.539. Let's see what that gives. 1 plus 90 divided by 365, but sorry, again, 1 plus 90 divided by 365 times 0.03539 equals times 991.35. Okay, as you can see, it's almost perfectly 1000, which is great. I guess the difference comes from rounding. This was a check. You get the true FV by using this AOR. So this AOR is our 365-day equivalent to a discount rate of 3.46. Okay, you need to be able to do that conversion potentially in the exam. So, quite a lot to do, to be honest, here in this lesson or in this section of the curriculum. we've dealt with the problem of DR versus AOR, 360 versus 365. You know that the way to go if you want to make comparisons is to convert into AOR using the 365-day convention. That's the bond equivalent yield. But at the beginning, at the top of the lesson, I also wrote that instruments contain no compounding in them, right? It's just scaling up linearly. And that's all very good. If you're just trying to compare instruments to one another, that's absolutely fine. However, there is a problem when you're trying to compute the yield on a money market instrument, which only sort of expresses things in terms of simple interest, with yields on bonds. Then you're not going to be able to make direct comparisons because yields on bonds are computed assuming some element of an element of compounding. So let me just finish off. Your book kind of discusses this, but doesn't really include any proper questions or examples on it. At least I didn't find any. So I don't think it's likely to be examined. I nevertheless want to show you how it's done. So let me say over here that it's also possible to convert to a chosen periodicity, e.g. a periodicity of 2, which you'll typically find in the US or in the UK, that's to allow basically comparisons, as I just say, with YTMs on bonds, which are computed on that very often on that semi-annual bond equivalent yield basis, right? So what we just did over here, this rate, okay, let me drag it down. This 3.539%. This is absolutely computed using simple interest, i.e. no compounding. So it wouldn't be directly comparable to a yield on a bond. The periodicity assumed here when we were doing this example, because of this scaling factor, was 365 divided by 90. So effectively, that's the year divided by the days. That was our implicit periodicity assumption, although we didn't actually state it as such. You should remember from a previous video that we covered a formula that I used to convert YTMs expressed with different periodicities, and it's a very universal formula. It comes up in more than one place in the curriculum. The formula was 1 plus APR computed with a certain periodicity divided by m to the power of m equals 1 plus APR, annual percentage rate, with a different periodicity n, raised to the power of n. So what you could do here, as I told you, your book just discusses this. It doesn't really provide a proper question on it, or even a proper sort of example on it, is say, why don't we take this 1 plus and stick as the APR 0.03539 over here, divide that by the periodicity of this computation, which is unfortunately this rather cumbersome number, 365 divided by 90, and you also have to raise to the same power, so 365 by 90, and that should allow us to compute an APR with a periodicity of 2, which is the semi-annual bond equivalent yield, divided by 2 to the power of 2. Now, quite a lot of stuff that we need to do here, but in the end, you end up with an APR 2 equal to 1 plus, this is 0.03539 divided by 365 divided by 90, okay. Of course, raised to the power of 365 over 90, and you are taking the square root of this. So effectively, you're taking, well, you don't need the 2 over here if you just do the root symbol. It's an implied exponent of 2. However, this is the same as raising to the power of 1 over 2, isn't it? And deducting 1, but also multiplying out by 2. So, it becomes a rather cumbersome formula to apply, to be honest, but let's try it. I'm going to start off with what's in the blue bracket, or maybe with 0.03539 divided by, open bracket, 365 divided by 90, close bracket. Okay. Press the equals key. Now raise this whole thing to the power, oh, don't raise it yet. Sorry, again, 0.03539 divided by, open bracket, 365 divided by 90, close bracket, press equals, plus 1. Now raise this to the power of, open bracket, 365 divided by 90, close bracket. Okay. Take the square root, deduct 1, right, and multiply the whole thing by 2, and we get, this looks like the right answer, 3.55%. And as you can see, it's very, very close to our original figure, 3.539. Now, to be honest, in the exam, I don't think they're going to test you on this. The result will be very close. So, let me say, typically only a small difference. To the AOR that we were starting with. And that difference is going to be small, especially if the interest rates are quite low. With low rates, you're not going to get much of a difference. If they were, higher double-digit figures, you would see a more of a difference. And just as a safety check, a sanity check here, because with the compounding assumption in place, you're going to get a slightly higher result in this case than you would without the compounding. But don't worry about it too much. I don't think you're going to get this tested. You're not going to get tested on this in the exam. You, however, need to be able to convert between DR and AOR and absolutely feel comfortable applying these formulas for PV, FV, as well, FV in the case of add-on rates, as well as the DR AOR computation.